This meeting is being recorded.
In problem 23 from chapter 10, we are asked to propose a efficient synthesis. So efficient, meaning if there are multiple pathways that we could take to create these compounds, we want to choose the fastest, the one with the least amount of steps. So that's what we will do for these transformations, these changes in functionality of these compounds. So for A here, let's see if we can do this retrosynthetically. So we're going to look at our target molecule, which has that double bond, and figure out a way that we could create that. So an elimination reaction is one way to go from an alkyl halide to a alkene. So let's keep that in mind. And our starting material here is just an alkane. So we could functionalize that alkane, and by bromination, right, we could use something like Br2 to brominate this through radical bromination. And we could end up with a tertiary alkyl halide here. And from there, we could do an elimination. We want our final product to be a Hoffman product, if you recall. So the double bond for the alkene will be the less substituted double bond possible through elimination. So we would need to use a bulky base, so something like tert butoxide potassium could be used to accomplish this, and we could end up with that Hoffman product. Double F, right? MAN, Hoffman product, using tert butoxide. So that is how we could accomplish this transformation from our alkane to an alkene in molecule A. Let's take a look at B. So we have our same starting material, that alkane, and we need to get to the same spot here, a double bond, an alkene. But we're going to follow a different pathway at the end. We could brominate or chlorinate. We could do either. So we could use Cl2 as well to create a chlorinated, a tertiary alkyl halide. So we could use Cl or Br here. Either one is fine. Here, let's stick with bromine since that's what's written in as our reagent. And from there, if we want to get to our alkene product, it is now a Zaitsev final product, right? The more highly substituted double bond. So we can use, instead of a sterically hindered base, we could use a more linear base. So something like sodium methoxide, sodium ethoxide, we could use to accomplish our Zaitsev elimination here. Our Zaitsev product could be produced. When we get to C here, now we have to take our alkane, our cyclic alkane. So we have our cyclopentane as our starting material. And we want to create the substituted ring with a thiol group here. So if we do a retrosynthetic analysis, we could remove this bond here, and we would notice that the more electronegative sulfur atom, this could serve as a nucleophile. So we can place a partial negative charge there, and then on this other site, we can place a partial positive bond. So this would have to be our electrophile site over here. So how can we create an electrophile from our cyclopentane? Well, we could definitely brominate it again. So say we did that. We could use Br2 and light, for example, here. And then we would end up with this cyclic alkyl halide. So we have bromo cyclopentane now. And we need to perform a substitution, right? So we can then use something that has that nucleophile to substitute. So we could use something like this sodium thiol, NaSH here, and we don't have a competing elimination reaction with this reagent because the SH, this guy here is a strong nucleophile, but not a strong base. So we would just see a substitution and our target molecule here. So for the last example, let me erase some of these spots here. Let's see if we can squeeze in D down below. So for molecule D, we have the same starting material, the cyclopentane, but now we want to end up with a diol, a cis diol product specifically, right? A cis diol. So it has two alcohol functional groups and they are in cis orientation. So if you recall from, let's see, that was chapter 9, we could have an alkene and end up with a cis diol using certain set of reagents. So let's see if we can get to that point, if we can create an alkene out of this. So in our first step here, we could functionalize this, brominate it. So we have Br2 and light. That gives us this compound here. Then we can do an elimination to form an alkene. So what do we want? We could use tert butoxide again, potassium here, and that would give us this next product. And then our final step here, we can use, if you recall, cold potassium permanganate. So that would be in cold conditions, KMNO4, and this would create that cis diol that we see in our target molecule. So both of these would be alcohol functional groups. All right, and that's no longer an alkene. That's just a dark single bond there. So you can see these are all of the efficient syntheses for compounds A through D, turning the starting materials into the target molecule that we see.